Some of the principles of analog signals interfaced to PLCs can be difficult to understand, but you actually do have some, I wouldn't say experience, but use of the concepts that are very important. For example, analog inputs have to be sampled in order to come into the PLC. The PLC is a discrete thing, right? It's on-off, and it can represent numbers, sure, and amounts of things. It represents them as, strings of bits. But how does that work in detail? And speaking of which, or speaking of inputs, what about outputs? How do outputs work in detail? Because the output needs to be a continuous thing. It needs to be an analog signal, and yet the PLC is a digital thing. So how does all this work? Well, the key to understanding all of this is something, I would say it's a concept that's called resolution. So there's resolution in amplitude and there's resolution in time, both of which are important to consider. And I think maybe the easiest way to understand this concept or these concepts on an intuitive level is to think about audio. Today we all use our phones for music players or whatever the case may be, but the music is stored or streamed digitally. In other words, it's just a string of ones and zeros. And that's not just any string of ones and zeros. It's very, very special and has to be interpreted in the right way to be your favorite song playing on your phone. But let's look at it a little bit deeper than that. Let's try to figure out and understand how the information gets into whatever machine it's used for processing the song and then is put back out. Now today we use compression quite a lot. And the compression is usually, well, it started out with MP3 compression back when I was in college or so, back in the late 90s or so. But different methods of compression are used. If you set aside the compression for a moment, because that's not really relevant to our discussion, we have to represent sound with ones and zeros. How would you do it? Well, how would you represent sound with numbers? Well, there's an easy way to do it and think about it, but you have to know a little bit about sound first. How does sound work? Well, sound is actually a longitudinal pressure wave. So as I'm talking, I'm recording this with a microphone. This microphone sits right above my camera, and it's just a dynamic microphone, and it's actually a classic rock and roll microphone, an SM58. It's kind of or used to be the workhorse of popular songs in any band. They're still widely used today, very common microphone. But it's called a dynamic microphone. The way it works, it's basically got a little round diaphragm. It looks like it's made out of shrink wrap or cellophane, and basically it's just a thin diaphragm, and when you talk, if you're touching it, you can feel it actually vibrate. It has such low mass that the variation in air pressure coming towards it from your voice will actually make it vibrate. So all you do is you just mount a coil of wire on the back of it, just magnet wire. It's very fine. Put it into a magnetic field, and as that diaphragm moves, it will generate a voltage signal. And then that voltage signal varies, above 0 and below 0 volts as the diaphragm moves in and out, as it moves back and forth. When it's moving one way, it generates one polarity. When it's moving the other way, it generates the other polarity. So all you really are doing is you're, in a way, electrically measuring the position of that diaphragm versus time. And that's what a sound recording is. It doesn't matter if you're putting that onto magnetic tape, which most of you have probably never even used. It doesn't matter if you're taking that and putting it into an analog to digital converter, which is something that samples the sound. In other words, it measures the voltage measures how high or how large the voltage is at various points in time. It doesn't really matter how you record it. That's what you're recording, is variations in air pressure. And what I've shown on the screen here is just my voice. It's me saying, welcome to MET 284. That's all it is. I won't play it for you. You've just heard it. But it's interesting because what this graph shows is, first of all, time on the x-axis, and then the y-axis is literally the movement of the microphone diaphragm back and forth. Okay, so I was going this way before, but if we think about it moving up and down if the speaker's faced upward, it's really just the movement of the diaphragm going back and forth. And to reproduce the sound, all you have to do is just amplify it, make it a larger voltage and capable of passing more current, and make a speaker move the same way. And the speaker will have the sound of my voice. You'll be able to understand it. It'll sound, depending on the quality of the recording and the speaker and so forth, it'll sound like I'm standing right there saying exactly what has been recorded. Now, it's kind of hard to understand because if you look at this, it just looks like a bunch of vertical lines, and they seem to vary all over the place. And if you've never seen anything like this before, it can be a little bit intimidating. Let me break it down for you a little bit. We don't need to see the whole thing. Let's zoom in on the first part here. This is where I'm saying welcome. And you might have guessed that the two big sections there, where there's a lot of variation and there's very small variation between, is welcome. Okay, that k sound. You might notice, if you've done anything with this, is that little bit of audio right in front of the second section. If we zoom in on this section, this is what you see. And so the first, about to where it's labeled 0.28 is well. And of course before that there's actually up to 0.06, there's silence essentially, maybe a little bit of noise. And the k sound for come is right at about 0.32. You see that little section there that looks like it's filled in. And the part of come is the last bit there from about 0.34 to the end. So this is welcome. Now the reason that there's more filled in area in the k sound is because the k is a higher frequency. And so there's more movement of the diaphragm back and forth really fast, whereas the well is a lower frequency, and the of come is a lower frequency content as well. So let's focus in on the well portion. So we zoom in on that, and we're beginning to see motion, right? You could imagine that the speaker moves up a little bit at first, and then down, then back up, and then it starts moving back and forth over time in this pattern that you see here. And of course, time's just going from left to right, and so once it's made all these movements, it's done, and it has made the sound well. Now let's zoom in on the very first portion of this. This is what's called a waveform. I'm going to zoom in on this little area I've got highlighted in red. And this is what it actually looks like. It's really made up of what's called samples. And what are samples? Well, samples are just where the analog to digital converter in the speaker card, the sound card in my computer, measured the voltage coming out of the microphone. It just measured it at various points in time. Now notice in the lower right hand corner, lower right hand corner of this window, it says 22050 16-bit mono. And you might recognize that, or it may sound familiar, especially if you've got any CDs, audio CDs. When audio CDs first came out, which I believe was in the 80s, I didn't have any until the late 90s or so, I think, but when they first came out, they were often advertised as being 16-bit, 44.1K, so 44,100 hertz. What did that mean? Well, it was kind of a marketing trick, really, because the 44,100 hertz is a frequency that if I were to play a sine wave at that tone, I don't think there's a human being alive that could hear it. It's too high pitched. There may be some animals that can hear it, but it's in the ultrasonic range. It's in an area that you can't hear. Most people have a hearing range from about 20 to 20,000 hertz, maybe a little bit north of that. And as they age, that range decreases. The range of frequencies they can hear decreases. In fact, I had heard, this was after my time, but apparently students in grade school, when cell phones became popular, wanted to be able to know when they were getting a text message or information. The problem is, if they left their phone on, teachers would know because they'd hear the phone ding or make a sound whenever the text message came in. And so what students would do is get very high frequency ringtones that were in a range of frequencies that their young ears could still hear, but the teachers, who obviously were typically much older, could not hear. And so your classmates would know your phone's going off, but of course they're not going to tell on you, and the teacher can't hear it anyway. So kind of a clever use of this idea. But as you age, the frequency range that your ears respond to goes down. You lose basically amplitude measurement at different frequencies. Anyway, so what this sound card's doing is it's measuring the voltage output from the microphone at discrete points in time. And you can actually see all the points on this curve. The curve itself is just an interpolation of all the data points. And we've zoomed in quite a lot here. In fact, this should be time on the x-axis, and if I remember right, it's seconds. So 0.106 seconds would be 106 milliseconds. If I had a calculator, I'd run the math, but you can do this if you want. I didn't finish what I was saying about the frequency range. So CDs are supposed to be 44,100 hertz. And really, that was an excessive frequency. It was unnecessary because people couldn't hear that high frequency. And so what it really meant was there were two channels, a left and a right, stereo in other words. Each one sampled at a frequency of 22,050 hertz. And that's about the upper limit of any human being's range, and so there's no point in recording anything after that an instrument produces, because human beings couldn't hear it anyway, and the purpose of music is for human beings to hear it. So the 22,050 just means how many of these voltage measurements are being taken per time. That's quite a few, right? 22,050 samples every second to represent the music. And then the 16-bit just represents the discretization in amplitude. So in a PLC, again, you can't record a continuous signal, right? You have to break it down. You have to estimate it. You have to round it off. So you can't record the exact position of the diaphragm. There's going to be some error. Basically, think of the diaphragm's motion back and forth as being broken down into steps. And so the sound card can only record certain positions because it only has certain steps. Now the number of steps it has available, and so the precision with which it can represent the position of the diaphragm is fairly high. That's what the 16-bit portion is all about. If the 16-bit means that each one of these samples has 16 bits associated with it, 16 bits that are recorded. That's the thing that is recorded for each sample, and it's just assumed that these samples come along at a rate of 22,050 per second. So that's how fast you have to play it back. By the way, if you play it back slower than that, it sounds like the pitch goes down. So you can make your voice sound like Darth Vader by decreasing the speed of playback. But anyway, so the 16-bit, that means there are 16 bits associated with each sample to record that sample that is the sample. And with 16 bits you can record 0 to 65535. So that's 65,536 different positions, including the neutral position, okay, or the zero position in the extents. And so what this means is that remember I was talking about the microphone's diaphragm's position being discretized. Well, it's discretized into 65,536 different positions, which is pretty doggone good resolution. It's not bad at all. Here's an experiment you can perform. If you actually still have a CD player somewhere, and you have an audio CD, some songs, it was popular in the past to fade out. So you would, the band would be playing along, you get to a chorus, the song's pretty much done, right? You don't know what to do with it, so you don't just end it. You fade it out. So you perform a logarithmic audio or amplitude fade so that the singer kind of fades away and the music fades out, and that's it. Well, if you have a CD like that with a song that fades on it, be careful when you do this, because you don't want the next song to come on and be very loud. But what you can do is put it into your CD player, and as the song is fading out, turn up the volume. Now make sure that when the song's gone, before the next one starts, you turn it back down, but you'll need to crank it up quite a bit. And as the song fades out, what you'll notice is the sound becomes more and more scratchy. The reason for that is because the waveform itself is decreasing. Now the resolution's not changed, right? The entire range from speaker all the way as far as it can go this way to all the way it can go this way. One position 0, the other one 65535. Okay, so if the speaker is being made to move back and forth at a lower amplitude, which is what makes it sound like a lower volume, then the number of positions it has available over that constrained range, that smaller range as it fades out, is smaller, and so the precision of measurement goes down. And as you boost the volume, you'll hear it become quite scratchy towards the end. So it's just an experiment you can perform if you're interested in it. So the point here is that we're giving up something, right? We're trading off the continuous signal, the actual signal from the sensor, in this case a microphone. We're trading that off for a version of that signal that has been discretized in amplitude. Pretty good resolution. I mean, what if you have a tank and you're trying to measure the level in the tank? So you've got a level sensor. If you could have 65535 or 65536 different heights in that tank, that's probably adequate, right? You might want to grab a calculator and see what resolution it would be. It's pretty simple. Say you've got a 10-foot tank and 65536 different positions. Just take the 10 feet and divide it by 65536. That's how much change in feet the tank would have to experience in its liquid level in order for the number coming into the PLC to change. It's pretty small. So this would not be bad resolution for the sensor, for level in a tank. Now if you're talking about the distance between the Earth and the Moon discretized into only 65535 different levels, that's going to be a much longer distance per change, or per least significant bit transition. And what that really means is, when you've got a 16-bit number, what happens is the least significant bit is constantly flipping back and forth as the count that string of bits represents increases. So if you think of a counter or something in the PLC language, as you increase the count, there's a place in memory that the number just keeps going up. And so that's what we're doing here. We're dealing with numbers. And as our position goes up, the least significant bit keeps flipping along with all the other bits eventually to represent higher and higher numbers. So anyway, I hope this helps you understand that the amplitude is discretized, but also the dimension in time. Time is discretized here. Notice that the waveform is not sampled at all times. It's only sampled at discrete times. Now again, 22,050 times per second is pretty doggone fast. Most industrial processes do not have near this amplitude resolution or this frequency resolution. And the reason is because it's simply not needed most times. If you have a process where you've got some heating process and you're measuring temperature, the temperature range is going to be set that maybe you need a 1,000-degree range. Well, a 1,000-degree range, if you have an amplitude resolution of 65536 or 16-bit, all you have to do is take the 1,000 degrees and divide it by 65536, and that's how much the temperature would have to change before you'd recognize that the temperature had changed at all, because it's been discretized in amplitude. You should grab your calculator and run through that just for fun. 1,000 divided by 65535 or 65536, it doesn't really matter, take your pick. But that's the resolution, or how much the temperature would have to change in order to detect that the temperature has changed. Now obviously you're not trying to measure the temperature from absolute zero to an infinite temperature. You got to decide on a range, but in that range the resolution would end up being pretty good. And as a matter of fact, most PLCs analog inputs and outputs are either 10 or 12-bit. They're not 16-bit. So with 10-bit you get 1,024 different steps. Every time you add a bit it doubles the resolution, but with 12 bits then you get 4,096 different steps. And again, that's quite often adequate for most processes. Now as far as sampling frequency goes, that's a little more complicated with a PLC, because it depends on whether or not you've got a special input that's tracking it for you, that's automatically doing it, or if it's relying on getting to that point in your code where it goes out and measures it. So, and it's not like it's measured in your code. Really, it has to do with the PLC scan time. So, PLC program, a ladder logic, is scanned, and it takes a certain amount of time to scan it. And then, of course, there's reading inputs, setting outputs, and doing overhead. So that all of that time it takes is, gives you an idea of the frequency of how often the sensor is looked at or sampled. So it's important to understand that these analog signals are going to be discretized in amplitude and in time, because they'll just be sampled every time the PLC goes back and looks at the inputs, which doesn't happen at all times. Now if you've got a process that responds a lot faster than the PLC is capable of watching, you need some other system. You need some way of dealing with that. Now there are so-called high-speed inputs. They are typically for the digital world, not the analog world, where you have a counter or something that, if you've got really high frequency pulses, it can count it because the scan time of the PLC is too long and will miss a bunch of the pulses. But in the analog world, I'm not really aware of any high-speed inputs that automatically track the signal, because really the idea is that the PLC needs to be able to respond to it in real time. Most of the time you're doing PID control or something like that. And we haven't talked about PID control in the class, but that's the control algorithm most commonly used for continuous signals.